All right, so I wanted to make a review type of notes for you, and I don't have any worksheet or anything that you need to be looking at the same time. It's mainly just I kind of started it in class when I started talking about the differences between x versus t and v versus t graphs, and really that's what I want to look at. So what what you need to do when you're given a x versus t or v versus t graph. So let's start with a position versus time graph. And you can just write this down in a separate sheet of paper. These are also known as x versus t. When you're given this kind of graph, t is always on the x-axis, x is always on the y-axis. You have three things you need to, or three types of questions you can answer. The first one is a right there question. These are things like distance, displacement, what else? Position. When they ask distance questions, it might be something like how far. When they ask displacement, I like using the formula delta x equals xf minus xi. Then the next things you need to do when you're given a graph of x versus t, the next type of question, sometimes information is hidden in the graph, and it's hidden always in two places. The first one being the slope. Slope for any graph is always the same. Slope for any graph, right, is, let me write it just like this, that m, or the slope, is equal to the change in the y-axis over the change in the x-axis. Now what changes with every graph is what's on those axes. So for this graph, we have position on the y-axis, and we have time on the x-axis. So that right there lets you know what slope is. And here's where, if this was a test, you would use your formula sheet and find, well, what is delta x over t? And you could see that that's equal to velocity. So all right, so there you have it. So slope is velocity. You can then also write that when you calculate velocity as splitting that delta x up into xf minus xi over tf minus ti. Okay, the third thing you want to look for, the third thing is the area. Now, once again, just like slope, you always do it the same way, right, with area. You just take a base and a height and you multiply them. When you take something, though, like base, when you take something like area equals base times height, you're really saying then that the area is equal to the base, or the x-axis, times the height, or the y-axis. Well, okay, well, what does that mean for a position versus time graph? Well, the base would be time and the height would be position, right? So we have the x-axis being time and the y-axis being position. And what happens when you multiply time times position, right? T times x. Well, let's look at the units, right? If you multiply, say, seconds by meters, you get second meters. And if you think about that, that's pretty illogical, right? It doesn't really mean anything. You don't usually multiply a time by a unit of distance. Now you might say, well, when I drive to school, I drive 25 miles per hour. But there, the per is the division sign, and there's no division sign going on here. So this is different right here, 25 miles per hour. This area here is saying you take your time and you multiply by your distance, and that just doesn't make sense. So actually the area ends up being nothing useful, meaning it's just meaningless. So this is why when you're given a graph, you need to look at it and be able to know what are the right there things, right? For instance, distance, displacement, position on the x versus t graph. What does the slope mean? In this case, velocity. And what does the area mean? In this case, nothing. All right, and that's how you do your check there for this kind of graph. So let's look at an example, right? So if I just make up an example here, I'll try and maybe make it similar to something we've seen maybe on a graph in class. Let me see here. What do I want to do with this? Maybe something like that. And we'll have the position versus time graph go up like this, down like this, and then we'll have it go into the negative, and then we'll have it go right here. Okay. And I'm just totally making this up, right? I mean, there's no rhyme or reason for it. I'm just trying to give us something here that we can talk about. All right, a little bit of a, it's not perfect looking, but you get the idea. All right, so I'm going to try and make this pretty symmetrical if I can. So maybe, I don't know, 1, 2, 3, 4, 5, 6, 7, 8. Let's go 9. This is where I'm not quite sure. I might get burned a little bit for not making this perfect, but you can get the idea. All right, so here we have time on, whoops, I don't know what happened there. Here we have time on the x-axis, and on the y-axis we have position. Now, what are these positions? Let's say, can we do here? Let's just put some, let's see if we can get away with this. We'll put 0 here. We'll say +5 here. We'll say down here, I don't know, -3. And we'll just try that. All right, something simple like that. Okay, so some right there questions. One might be in 14 seconds, right? Which is the object is at 14 seconds right here, right? Here's 14 seconds, right? In 14 seconds, how far does the object move? All right, so if this was the question, in 14 seconds, how far does the object move? Well, it would move in the first 4 seconds, right? Right up to here, first 4 seconds. It would move from 0 all the way up to +5, right? So it would move 5 meters in the first 4 seconds. Then in the next 4 seconds, right, to get to 8, it would go, or to get to 8 seconds, yeah. So from 4 to 8 seconds, it would go 5 more meters, right? Because it's going from 5 right here, +5, all the way back to 0. All right, then in the next 2 seconds, from 8 to 10, it gets to right here to -3. How far is this? Well, it was at 0 at 8 seconds, and now it's at -3, so it moved 3 meters, right in this distance right here. Then from 10 seconds all the way to 14 seconds, it just held position, right here. It didn't go anywhere. Sure, time passed, but it didn't go anywhere. So this is actually going to be a distance of 0 meters right there. So total distance, so let's write this down. Let me switch back to black. So we're saying total distance in 14 seconds, right? Which is why it's the total distance, is 5 meters plus 5 meters plus 3 meters plus 0 meters. What does that equal to? 13? All right. And there's how we would, there's one way we could get a right there question. Another one would be displacement. What is the displacement at the following times? And I'm going to pick some times. I'm going to say 4 seconds, 8 seconds, 10 seconds, and 14 seconds. And for all of these, we're going to use one formula, right? And that is delta x is equal to xf minus xi. So for 4 seconds, what is my xf, right? xf at 4 seconds, 4 seconds is right here where I'm making this dotted line. And xf is going to equal 5 meters, right? It's right at this dot right here. Xi, for all of these, is going to be 0 meters. So we're assuming that xi will be times 0. Okay, so if that's the case, then down here, my delta x for 4 seconds would equal my final position of 5 meters minus my initial position of 0 meters, which is positive 5 meters. At 8 seconds, now what is my xf? My xi is still 0. What is xf now? At 8 seconds, we're right here at the x-axis. So we have no height. We have no, or the position, we have a height or a position. It is 0 though. So 0 is just the location, just arbitrary, right? So here for this one, we have a final position of 0 meters minus an initial position of 0 meters, which is 0 meters. At 10 seconds, our location is what? Well, here's 10 seconds. What is this location? -3? Okay. So if that's the case, then final position is -3 meters minus the initial position, which is 0 meters, is equal to -3 meters. Finally, at 14 seconds, we see that the final position is still -3 meters, right? This is 14 seconds right here. So that would mean that we once again have -3 meters still minus 0 meters is equal to -3 meters. Okay, so this is how far in a direction from the original location is what displacement is asking. So what we saw is at 4 seconds we were 5 to the right from 0. At 8 seconds we were at 0, so we actually had a displacement of 0. At 10 seconds we were 3 to the left because we were at -3. So our displacement was -3. And at 14 seconds, we were still 3 to the left. And that's why our displacement was -3. All right, so that's kind of the idea there. I think we got all of those. I might also ask a question just about position. I might say, at time 4 seconds, where is the object located? And if they said that at 4 seconds, you would say the object is located at +5 meters. All right, that's it. Okay, let's look at the next thing we can get next kind of information we can get from this graph, and that is velocity, right? Velocity is the slope. So we actually have a slope right here that I'm going to calculate. Let me see if I can highlight it. Let's go with this slope right here. Now this is a positive slope. It goes up and right. And so to calculate this, they might ask you the question like such. They might say, what is the velocity of the object at 3 seconds? 3 seconds is right here. Let me see if I can get a different color. Maybe orange. All right, here's 3 seconds. I'm making this orange line. It's kind of crazy. Put an orange star right there. All right, so this location right here is 3 seconds. Now, at 3 seconds, we want to know what is the velocity right here. And to get the velocity right at that point, we need the slope of this green segment, right? So the question is, once again, velocity. Let me draw a line here. At 3 seconds. All right, so to do this, we're going to use our formula V equals delta x over delta t. We're going to expand it out into xf minus xi over tf minus ti. And that's going to give us our velocity. But what are the final and initial positions, the final initial times? So if we go back up and look, on this green segment, we just pick two points, one to be final, one to be initial. And it can be any 2 points. The only caveat, or the only thing we got to watch out for, is that the final position has to occur at a later time. So I'm going to pick the very end points. Here's a blue dot here. Here's a blue dot here. So I'm going to say that my final time then, if I follow this blue dot down, I don't know if you can see those dots. I'm trying to follow it down to the x-axis. That final time is 4 seconds. The initial time is right here at the origin, so it's going to be 0. So I always fill the times in first because it makes my life a lot easier. So I'm saying right here, my final time is 4 seconds minus my initial time of 0 seconds. Locations, well, at 4 seconds, our location, right? Here's 4 seconds, follow it back up, follow it over. Our location is +5 meters, right? Okay. So make sure that makes sense to you, why that's +5 meters, right? Where this black dot is right here it's at position +5 meters. So that would be final because that's the one that occurs at 4 seconds. All right, what is the initial position? Initial position is where the object is at 0 seconds. So at 0 seconds here, looks like the object is at 0, right? Okay, so we can go ahead and say minus 0 seconds, or meters, sorry. Jeez Louise. It's getting late. That's what I get for making this video so late. I'm waiting to the end of the night. There we go. I'm sure it'll still be a great video. All right, so anyways, okay, so we have our velocity is equal to that. All right, so we have velocity is equal to 5 meters divided by 4 seconds, which is equal to, well, 4 goes into 5 one time, and there's 1/4 left over, so we could say 1 1/4, or we could say 1.25 meters per second. And it's positive, right? It's up and to the right. Okay, good. This pen's struggling a little bit. So that's pretty much it, right? And obviously, if I did the same thing on this line right here, let me see if I can get a different color. Maybe use the yellow highlighter. If I did the same thing over here and found the slope right here of this yellow segment, I guarantee, or it should be symmetrical, right? So meaning instead of being positive 1.25, it's going to be negative 1.25. What would that look like really quick? Well, I'd probably just have to pick a final position right here, initial position right here. So 8 seconds minus 4 seconds, 0 seconds minus 5 seconds. So I think I would get something that looks like this. I would get V equals, let's see if I can write this out, XF minus XI over TF minus TI. This is struggling a little bit. I'm not sure if I just need to reset this program or what. Oh, I see what's wrong. The stylus, the tip on the stylus was coming off, so the computer doesn't recognize it then. All right, XF minus XI over TF minus TI. So we would say, I think our final time was 8 seconds. Our initial time was 4 seconds. Final position was 0 meters. Initial position was that positive 5 meters. And so now you can see, right, that you have to subtract that 5 meters. So you end up getting a velocity of negative 5 meters per 4 seconds, or negative 1.25 meters per second. All right, so the velocity isn't always going to be positive, right? The slope isn't always going to be positive. And this just indicates direction. Maybe positive is to the right, negative is to the left, and so on. So you get these two slopes here, the green one being positive 1.25, the yellow one being negative 1.25 meters per second. All right, good. Hopefully there's no questions there. We kind of went over that in class already, but I wanted to do a review again because we did not talk about the next graph, and I wanted to make sure you understood this. So the next graph is velocity versus time. All right, same thing applies. When you have this graph, right, what does it look like? First of all, it has velocity in meters per second on the y-axis. A lot of times this one, too, will dip into the negative. You have 0 happening right here at the x-axis, and then anything under that being negative velocity. Okay, so then on the x-axis, you have time in seconds. Okay, so far so good. Let's look and see what else. Okay, so this is also known as V versus T, right? This is the same thing as V versus T graph. All right, let's go ahead then and talk about the 3 types of questions they're going to ask you. One is going to be a right there question. Another one is going to be, or a type of right there question would be, what is the velocity at a certain time? What is the speed? at a time. It might ask, when is the object stopped? All right. They also might ask, when is the object speeding up or slowing down? But I usually don't ask that question a ton. Those get a little tougher. But yeah, what is the velocity at a certain time? What is the speed at a certain time? When is the object stopped? Another question might be, when is the object moving in the forward direction? And when is the object moving backwards, right? Things like that. So let me write that down. When maybe one would be, when is the speed constant? All right, so it seems like we have quite a few questions that can be right there with this one. I'll try and cover those. The next thing is just like the last graph, right? The next thing we can talk about is slope. Slope is the change in the y-axis divided by the change in the x-axis. Well, what is that for this graph? On the y-axis is v, on the x-axis is t, so we can say that this is going to equal delta v over delta t. This is also known as what? And this is where we have to get our formula sheet maybe in check, but it's also known as acceleration. So acceleration is the slope. All right. And acceleration can be positive or negative, right? This describes whether you're speeding up or whether you're speeding up in the positive or negative direction. I'll write that down. And maybe I should say it a little differently, right? Acceleration describes whether you're speeding up or slowing down. In the positive or negative direction. And this is kind of tricky because let me give you an example of why. Let's say you throw a ball up in the air. Ball goes to the top, stops, comes back down. Something like this, right? So the ball is heading upwards, the ball stops, the ball is coming back down, and that's the whole point of the motion right there, right? Or the whole extent of what happens. When the object is traveling through the air, we know that the acceleration only points downward like this. And maybe it's equal to negative 9.81. And we know that when the object is traveling down, it's speeding up. So what I'm trying to show you is that negative acceleration, negative 9.81, is the same as when the ball is traveling down, right? It's moving downward. You can see this velocity. It's moving downward and speeding up. Okay. But negative acceleration also occurs when the ball travels up. So what I'm trying to say is negative acceleration or acceleration downward also occurs when the ball travels up and slows down. So it's when the ball is slowing down while going up. All right, so these are both negative acceleration. So what I'm saying here, or trying to say, is that slowing down in the positive direction is the same as speeding up in the negative direction. Okay, so that was a little bit of a tangent there, talking about acceleration. So everything right here within these two blue lines was a little bit of off topic, but that's okay. I just wanted to mention it, and it didn't hurt to go over it. So getting back on topic then, the slope is equal to the acceleration. All right, what about the area? Last time the area didn't do anything, right? It was nothing for an x versus t graph. But what about now? Well, area is always the same as what it was before, right? We said the area is equal to base times height. If it's a triangle, 1/2 base times height. Well, the base is whatever's on the x-axis. The height is whatever's on the y-axis. Well, let's look at our graph, right? X-axis is what? T. Y-axis is what? V. So what happens when we multiply time times velocity? That is going to equal our area. But what is time times velocity? Well, what happens? Let's take the units. What happens when you multiply, or let's do this. Let's think about a formula for velocity. Well, let's go ahead and multiply both sides by t. And what you can see is that we get this. Delta x is equal to delta t times v. So when you multiply t times v, you get delta x, or displacement. Or you could also call it change in position. So our area tells us change in position. Let's go back up here and look at that. So I'm saying that the area is equal to delta x. Can I prove that with units? Yeah. Let's go back and look at that. So if we multiply, I'm going to erase this for a second. I'll rewrite it down here. Whoops. All right, if we multiply the units of time by velocity, we see the area will give us, whoops, keep looking for the highlighter. Area will give us meters. So this is why the area can be things like displacement or distance. And technically, it's always going to be displacement if you do it right, but sometimes it can be distance. So questions, they might ask for area, right? What are some questions? They might ask, what is the total displacement? What is the total distance? They might ask at they might ask, what is the displacement between 2 times? They might say, what is the displacement at a time? All right. So those are some questions that can be asked there. All right, good. Let's look at an example, right? I think we can... Oh, can we use that one up there? I think I have enough room. Let me draw this. Okay. So what we have is something like this blue line. Let's go ahead and put some points on here. All right, it's getting a little rough to look at, but try the best we can. All right, when we make this or have this graph, right, and they start asking questions like the ones underneath it, right? What is the velocity at a certain time? Let's say the question is, what is the velocity at 4 seconds? All right, and so let's change that to, let me get a different color here. So if the question is at 4 seconds, then the velocity would be what? Well, let's follow it down. So here's 4 seconds right here where I'm making this blue dot. I'm going to follow it down to the line. The velocity would be whatever this point is, which I forgot to give a value, so I better do that. Let's say that this value right over here is -2. And up here, +2. All right, so therefore, the velocity at 4 seconds is -2. Okay. So let's write that down. At 4 seconds, it would be -2 meters per second. What is the speed at, say, 4 seconds? Okay, so this next question, if we keep with at 4 seconds, then the speed, this was velocity, speed would equal the absolute value of the velocity at 4 seconds. Well, what was the velocity? We just said it was -2. So what's the absolute value of -2? Pretty much all you have to do is just make it positive. So the velocity at 4 seconds would be positive 2 meters per second. And that's kind of the idea there. So, so the velocity at this point, let me highlight it here in green, at that point right there is -2. But the speed is +2 because the speed doesn't care about direction. And this negative sign over here is giving us a direction. It's telling us backwards or left or down or something like that. Okay, next question. When is the object stopped? The object is stopped anytime the velocity is 0. Let me write that down. So when v is equal to 0. And it could be more than one time when velocity is 0. But if we look at the graph we made, right? The velocity is 0 when? Well, right here. This is when it crosses the x-axis at time 3 seconds. So it's just for that one split second of time that it stopped. So we can say at time equals 3 seconds. All right, the next question. When is the object moving forward? All right, the object is moving forward anytime its velocity is positive. Well, when is the velocity positive? Let's go back up here and look. If I get my highlighter out, the velocity is positive anytime the line is above the x-axis, which is right there in yellow. The velocity is negative anytime the line dips below the x-axis and into the negative portion of the graph right here. So what times is the velocity positive? Or when is the object moving forward, right? We would say from time 0 to 3 seconds, that yellow line. That's when it's moving forward. Let me get my blue marker again. And this we said from t equals 0 to 3 seconds. Or I'll just write 0 seconds to 3 seconds. Hopefully you can see that okay. That's getting pretty, I don't know, pretty, there's a lot written right there in one space. Pretty congested. All right, when is the object moving backwards? Well, this would be when the velocity is negative. All right, so when is this? Well, this would be the purple line. So we could say now from 3 to, what is that, 6 seconds? All right, and then finally, when is the speed constant? When does the object hold speed? So it looks like it holds speed at a couple different times, right? And I think I'm going to need a different color marker here. It holds speed from 0 to 2 because we have 0 slope. And it holds speed from 4 to 6. So pretty much we're saying it holds speed when the slope is 0. And slope is 0. And the answer here would be 0 to 2 seconds, 0 seconds to 2 seconds, and 4 seconds to 6 seconds. Okay. All right, so hopefully there's no questions there. Once again, what is the velocity at a certain time? Just kind of find that point. So if it's 4 seconds, You can say it's -2 because you just follow the graph, read the graph. What is the speed at a time? Speed is the absolute value of velocity. So we took that -2 because we talked about 4 seconds again. We took that absolute value of -2. We got positive 2 meters per second. When is the object stopped? This is when the velocity is 0, that we have a stop. So this was 3 seconds. When is the object moving forward? Forward is synonymous with positive velocity. So that's how we got that question, 0 to 3 seconds. When is the object moving backwards? This is synonymous, backwards is synonymous with negative velocity, so 3 to 6 seconds. And when is the speed constant? Constant speed is when the slope is 0. So that's how we knew that. All right, so hopefully that's making sense. I know that was kind of a lot. We'll go a little bit further here with slope and area, and then we'll call it good. So slope is they're going to ask for the acceleration. And I can just very briefly, without doing any calculations, just let you know that looking at this graph, right here, I have 0 slope. So this would be an acceleration of 0 meters per second, or meters per second squared. You can write it either way. I'm kind of partial to the meters per second way. But I know it's much easier just to write 0 meters per second squared. Then, right here, let me see, from on that squiggly wavy line, from 2 to 4 seconds, this is an acceleration that is positive or negative. It's going down and to the right. We should say the acceleration there is negative. And then finally, the acceleration is back to 0 right here. So let's go ahead and calculate this acceleration, this negative acceleration, right, at time 3 seconds. So something they might ask you is, what is the acceleration at 3 seconds? Well, if they ask you that, you have to then find the slope of this line in orange right here. All right, I know it's getting kind of congested on this graph, but we have to find the slope of this orange part, this middle part, right? This down and right part. And we'll just pick 2 points on it. I'm going to pick this point right here at 2, 2. I'm going to pick this point at 4, -2. All right, I'm going to pick those 2 endpoints because what I'm looking for, right, is 3 seconds. I want the slope. So anywhere on this orange area I'm highlighting, right, I can pick any 2 points, but because 3 seconds falls on that segment. All right, whoops. All right, so if we come down here and find some clean paper here, we're saying, what is the acceleration at 3 seconds? So what we do is we get our acceleration formula. We expand it out. We plug in numbers. Looks like my final time is right here, which would be at 4 seconds. Right, 4 seconds. My initial time is right here, which is going to be at 2 seconds. So I'm saying if that doesn't make sense, go back and pause it and look at that graph and see where I got 4 seconds and 2 seconds. All right, so at 4 seconds, our velocity, our final velocity is -2. At 2 seconds, right, our final velocity, or our initial velocity is +2. So we're saying it's going to be -2 is going to be our VF. And +2 is going to be our VI. What's -2 minus 2? That would be -4. divided by 2 seconds. Negative 4 over 2 is equal to negative 2 meters per second squared. Or we could say negative 2 meters per second every 1 second. That's how much you're speeding up by, right? Or you're accelerating by. You're increasing your velocity by 2 meters per second in the negative direction every second. Okay. All right, and this is the acceleration at 3 seconds. All right, that's how it's done. Let's get the area questions now. All right, area is a little bit tricky here. Here's why. A lot of students, when they get the area questions, which we learned area was displacement, right? That's what we said right here. Area equals delta x, because when we multiply the time times the velocity, we're left with meters. The area is going to be the area between the line and, or the curve or the line and the x-axis. So it's going to be this area right here in blue. And this area right here in blue. Now the area is going to depend on what times they ask us, right? If they ask for the whole time, we'll take all of that area. If they only ask for a part of the time, we'll just take a part of the area. Okay, so the questions we said we could answer with this are: what is the total displacement? And what is the total distance? Okay, so let's give this a try. What is the total displacement? All right, so to do this, I have some weird shapes here, and I need to split them up into areas I can take. So what I'm saying is, I'm going to split them up into, say, a square right here. Let me see if you can see this. All right, a square right there. A triangle right here. Another triangle right here. And finally, another square right here. Okay, so what I'm saying here is, by taking these 4 areas, we should be able to figure out the total displacement of the object. All right, what is the area? Well, for the first shape, it's base times height. The base here is 2 seconds. Multiplied, this is a square, rectangle, by the height, positive 2 meters per second. Cancel the seconds, and you're left with 2 times 2 times meters, positive 4 meters. All right, so far so good. Here's the trick. Look at this square right here. Once again, it has a base of 2 seconds, 4 to 6. Once again, it has a height of 2 meters per second, but it's negative 2, right? It's negative 2. So when you take a 2 seconds times a negative 2 meters per second, you should already see what the answer is going to be. Negative 4 meters. So this area right here, I'll try and draw an arrow because it's getting kind of crazy with all those lines. Negative 4 meters. All right. So we have two of our areas done, right? Positive 4 and negative 4 meters. Now we just have to get these triangles. Now you might say right away, well, those triangles are half those squares. And because of that, but are they? I don't think they are. Because my drawing is kind of not good. Yeah, I don't think they are. All right, let's just do the area. I think on my on my drawing it looks like they're half, but I don't think my drawing is very solid. All right, so anyways, if we get the area of this triangle, the area of a triangle is a little tougher, right? Area of a triangle is equal to 1/2 the base times the height. Well, the base here is only 1 second, and the height is positive 2. So we're saying then the area is equal to half of 1 second times the height, which is positive 2 meters per second. All right, notice what happens to the units. What happens to the numbers? 1/2 times 1 is just a half. 1/2 times 2 is just 1. So if that doesn't make sense to you, you can plug it in your calculator real quick. But that's just going to be 1 meter. So the area of this shape, of this triangle, right there, is going to be positive 1 meter. So far we have positive 4, positive 1, and negative 4. And by that same logic that we just did, this now is similar to the triangle we just did, but with a negative 2 meter per second height. We can now see that this triangle is going to have an area of negative 1 meters. All right, so there we have it. We have 4 areas. All right, we have the negative 4 and positive 4 meters, and we have the negative 1 and positive 1 meters. What is the displacement? The displacement is the total, is all of those displacements added up. That's what the total displacement is. So if I go back to the bottom, where I have a little room, total displacement is equal to positive 4 meters plus 1 meter minus 1 meter minus 4 meters, right? So we just add up all 4 of those displacements. You could have said positive 4 meters plus 1 meter plus negative 1 meter plus negative 4 meters. It's the same thing. All right, so the 4's cancel, the 1's cancel, and we're left with 0 meters equals delta x total. So this is the total displacement. Now, what's the total distance? Total distance is the absolute value of all of those displacements. We don't care what direction with distance, right? So now we're going to add up positive 4 meters, absolute value, plus positive 1 meter. And I don't have to write the positive sign. I'm not going to write it. 4 meters plus the absolute value of 1 meter plus the absolute value of negative 1 meters plus the absolute value of negative 4 meters. All right, see where this is going? All right, let's rewrite it then. Absolute value of 4 meters, just make it positive. It already is. Absolute value of 1 meter, just make it positive. Absolute value of negative 1 meters, just make it positive. Absolute value of negative 4 meters, just make it positive. Aha, so total distance here is 4 plus 1 plus 1 plus 4, which is going to be 10 meters. All right, so now you're seeing the difference between distance and displacement and how displacement is in the area. But if you do a little absolute value, you can also get distance out of it. All right, let's look at one more thing that a question might, kind of a sneaky question, one I like to ask sometimes to see if kids really understand this. Instead of asking the total displacement, I like to ask the displacement at a certain time to see if students really understand what's going on. So I might say, what is the displacement of the object at time? And I'll write this down. Displacement at time equals 3 seconds, we'll say. All right. Well, let's go back up to the graph, somewhere up here. At 3 seconds is right here, right? Right, the 3 right in the middle, right here at this point. So what we do, if we're just focusing on the displacement from 0 to 3, we just focus on this area. We don't worry about anything after it. And so here's 0 right here. Here's 3 over here. What happens, what's the area from 0 to 3 seconds? Well, this is fairly simple. Positive 4 meters for the square or rectangle, square, and positive 1 meters for the triangle. And that's it. So we just add that up. What's 4 plus 1? 5. So the displacement, trying to minimize this. Displacement at 3 seconds, right? So delta x at or in the first 3 seconds, that's probably the way it would be worded. Delta x in the first 3 seconds is equal to what? Is equal to those two areas, 4 meters plus 1 meter. Those two displacements, right? So we're going to get positive 5 meters. All right, so there you have it. Obviously, I can ask, infinite number of questions, but that's a pretty good sampling of everything that I can ask. All right, it's getting pretty late, so I'm going to stop it there and put this on Schoology for tomorrow. So, all right, have a good day. Let me know if you have any questions. This will be for before the review guide. You're then going to put some of this knowledge to use on the review guide itself of V versus T graphs and X versus T graphs. And then the next day after that, we'll talk about it in class a little bit if there's questions. And then we'll follow that up with a test. So hopefully this is making sense. You may have to watch the video twice. If it helps you. All right, that's about it. So take care.